number that gets multiplied. All right, everyone out there, we are going to continue with section 1.4 on exponents and unit conversion. So we've done various mathematical operations thus far: addition, subtraction, multiplication, division. In a lot of circumstances, we have a number that gets multiplied by itself several times. We have a special notation for this. We use this notation a to the power n. That number a we call the base, and that number n is called the exponent. So for instance, when I write 3 to the 5th, it means I'm doing 3 times itself 5 times. So that would be 3 times 3 times 3 times 3 times 3. Or we could also do this with a letter x, right? When we're using variables in algebra, it's basically just a stand-in for whatever number, right? So if you take some number and multiply it by itself 3 times in total, the way that we represent that is as x to the 3rd power, or sometimes called x cubed. We're going to have to review a couple of important exponent rules, because they're going to show up a little bit, particularly in the next section on scientific notation. So when I have a to the m times a to the n, so if the bases are the same, our rule is going to tell us to add the exponents. Why the heck would we do that? Well, let's look at a concrete example. Suppose I had 2 cubed times 2 squared. Well, what do each of these numbers mean? Well, 2 cubed is 2 times itself 3 times. 2 times 2 times 2. And 2 squared is 2 multiplied by itself. Again, there's 2 of those in all. So how many times is 2 being multiplied by itself? Well, I've got 3 instances here, plus another 2 instances there. That tells me I've got 5 in total. So again, we added up those exponents. And again, if you're curious, 2 to the 5th is 32. Powers of 2 are really important for various computing applications. Well, what about if I'm dividing these expressions? Well, and again, let's treat the example of suppose I had, say, y to the 6th over y to the 4th. Well, I'm going to actually explore this example and then get to the rule. If I have y to the 6th, that means some number y times itself 6 times. And then on the bottom down here, we have y times itself 4 times in all. Well, one thing we can do with fractions is we can divide out common factors from the top and the bottom. Well, there's 4 factors common to the top and the bottom, so we could get rid of 4 of them. All in all, we would only have 2 of those left. So we would be left with y squared. What did we do with the exponents? Well, we had 6 up here, we had 4 down there, we got rid of the 4 powers, so we ended up subtracting those things. So our rule here is that we're going to have a to the numerator power minus the denominator power. And everything in math happens for some reason, and actually looking at a concrete example oftentimes can help reveal why that's the case. Well, now let's suppose that the power in the denominator were actually bigger. So for instance, if we had b over b to the 4th. Well, that would mean we would have b over b times itself 4 times. Well, like above, we could go ahead and divide out one of the factors in both the top and the bottom. So I would still have 3 left in the bottom, so that's 1 over b cubed. What do I do with the exponents, and what even is the exponent? Well, one thing we're going to have to add in here to contextualize this is that when you just have a single power, just a regular old variable itself or a regular old number itself, you can always think about that as being 2 to the 1 power. What did we do? Well, there was still subtraction going on, but it looked like what actually happened is we took the power in the denominator and then subtracted the numerator, and those powers were represented in the denominator. So we get rid of all the powers in the top, and that means the powers we have left in the denominator are again going to be n minus m in this case. There's a couple other rules that we'll need to introduce here, and then we'll get some practice with all of these rules. Suppose we have 10 squared being cubed. Well, I've got multiple exponents going on here. We're cubing something. The thing that we're cubing is 10 squared. So anytime we're cubing anything, it just means take that number, multiply it by itself 3 times. Well, now I've got the same base here, and all of these exponents. Well, now we can come back up to what we did in the first rule. When I have the same base, it tells me to go ahead and add up all of those. After all, I got 2 powers of 10, plus another 2, plus another 2. That's 6 powers in all. So that'd be 10 to the 6th power. What's the principle that we can take away here? With those 2 numbers here, when we have those multiple exponents, we multiply those exponents together. Now, what about if we had a product of 2 things being taken to a power? So suppose I have 3x quantity being squared. Well, again, let's just think about what that means. Again, x you can think about as being sort of stand-in for some number. So taking anything and squaring it means multiplying it by itself. So we have 3x times 3x. Well, what's going on here? I've got 3 being squared and x being squared, because both of those things are being multiplied by themselves, which we could represent that as 9x squared. But for the purposes of illustrating this principle, we can observe that each of those parts of the product got taken to that power. So we can write that as being a to the n times b to the n. Now, what about if we had a fraction being taken to a power? Again, imagine we had 3/5 being squared. So one of the things we recall from working with fractions is when you multiply fractions, it's actually one of the easier operations with fractions. You just multiply straight across the top, multiply straight across the bottom. So you get here 3 squared over 5 squared. 3 times 3 is 6 squared. 5 times 5 is 5 squared. Again, this does equal 9/25, but for the purpose of this rule, the principle that we can observe here is that squaring a fraction or taking a fraction to a power means you just need to apply that power to the top part and the bottom part. Basically exactly the same as it was with multiplication. All right, well, let's use some of these principles here to go ahead and simplify an expression. So this is one of those things a lot of times when you're trying to describe phenomena, eventually you wind up dealing with variables and formulas, which we'll talk about in another section, and you'll need to simplify some of those expressions in order to get what you want. So there's kind of 3 different things going on here, right? There's the numerical part of this, there's the x part of this, and then there's the y part of this. So let's suppose we treated those 2 parts separately, right? When I have things multiplied, I can multiply them in whatever order I feel like. So I could first think, okay, well, what do I get if I have -5 times -2? What do I get if I have x times x cubed? And then what do I get if I have y squared times y? Well, -5 times -2, remember that when we take up negative times a negative, we get a positive result. So that'll turn to be positive 10. The x times x cubed, well, we have to think here, if we don't see a power there, we can always think about it as being a single power of that variable. And my first rule tells me to add those exponents. So that would be x to the 4th. Similarly for the y powers, again, I can always think about that as being one single power of y, in which case y squared times y would be, add those exponents up, we would get y cubed there. Let's look at some more examples here on the next page. Here we got some more complicated expressions. Let's see what we need to do with them. So we've got -3a b to the 7th over 24a squared b cubed. So then there's 3 different parts that we have to think about here. There's the numerical part, there's the a part, and there's the b part. Let's focus on the numerical part first. One extra step I could show to kind of break this thing down. I'll also show you some alternatives for what we do with a calculator. But we can note here, I've got a -3. That 24 we can really think about as being 3 times 8. So there's that factor of 3 in common. That's going to be important for simplifying the numerical part of this expression, because we can see we can cancel out or divide out that factor of 3 common to both the top and the bottom part. So that's one thing we can do, is divide out that power of 3. We'll still have 8 left in the denominator. Now what about the powers of a? Well, we see we have more powers in the denominator than in the numerator. Specifically, we have 2 powers in the denominator, 1 power in the numerator. Well, we can get rid of one of those powers in both the top and the bottom. So I've got a negative sign still hanging around here, but that a part will cancel, and we'll just have one single power of a left in the denominator. Now, what about our b terms? I'm still finishing out this expression. Doesn't make sense quite yet. Well, with my b terms, I have a positive number of powers, or sorry, a larger number of powers in the numerator than in the denominator. So we're again going to cancel out, divide out 3 factors from the top and the bottom. If I get rid of 3 factors from the top, I'll still have 4 of them left over. So that ending expression we will get here will be negative b to the 4th over 8a. You could write that as 8a to the 1, but you know what? It's simpler to just express it as being 8a. Another thing I'll mention here is calculators are actually pretty good at dealing with fractions if you're sort of fraction averse. When you have this expression negative 3 over 24, so here I'm going to use this little button here for the minus sign, so that's a negative sign as opposed to this one, which means subtraction. They do mean slightly different things, unfortunately, in the calculator. You can take negative 3 over 24. Now, you could express this in decimal form. That would be a completely valid way of describing it. Or what you could do is you could also use this fraction to decimal key. So if you hit the second button and then the fraction to decimal, it might be in a slightly different place depending on where your calculator, how your calculator's set up. But if we do that, note you get negative 1/8, which is the same numerical value that we saw in this expression, the negative part, negative 1 part in the top and the 8 part in the bottom. All right, let's look at squaring out a product. We talked about how squaring a product really just means square each part of it. So this thing would be a negative 5 being squared, a being squared, and then b cubed being squared. Well, negative 5 squared means negative 5 times negative 5. Well, that means I have 2 negatives, like we mentioned from last page. A negative times a negative gets us a positive, and 5 times 5 is 25. So I've got 25 and then a squared, and then b cubed squared. Again, we multiply those exponents together, and we'll get b to the 6th. Similar approach happens when we're talking about a fraction to a power, right? We're going to apply that fraction to both the top part, to the numerator, what we call, and to the bottom part, what we call the denominator. So we are going to cube both of those pieces. Well, again, whenever you have an actual numerical expression, you might as well actually cube out the number in this case. 2 times 2 times 2 is 4 times 2, which is 8. And then the denominator, well, this becomes, like we mentioned above, when I take something to a power and then to another power, I multiply those exponents. I'll get x to the 15th here. Turns out that the idea of doing an exponent actually extends beyond this. And in order to motivate this idea, I want us to kind of explore what happens when we take one number to a bunch of different exponents. So for instance, powers of 2. If I take 2 and I cube it, well, like we just said, 2 times 2 times 2 is 8. If I have 2 squared, it's 2 times 2, which is 4. And we also said that when we just have something to the single power, it just means itself. Now, what do we notice as we go up this table, right? As we go up, we are multiplying by 2, right? Well, what does that mean? That would mean whenever I'm going in the reverse direction, I would be dividing by 2. So let's say we want to continue this pattern. Every time we lower the exponent by 1, we are going to divide by 2. Well, again, let me do it, divide by 2 to go from here to here. If I divide 2 by 2, I just get 1. If I divide by 2 again, just trying to follow this pattern, keep it the same. 1 divided by 2, well, we could express that as being 1/2. So that is to say, 2 to the negative 1, based on this pattern, we can think about it as being 1/2 power. And then if we take this one step further, divide by 2 once more, well, when we cut 1/2 into 2, we get 1/4. So that is to say, we can think about 2 to the negative 2 as being 1/4. So this pattern that we've been picking up on is actually going to result in definitions that we have here. So we are going to define that a to the 0, so any number, when we take it to the 0 power, so when we have 0 copies of it in essence, we are going to call that number 1. And again, that's just to get it to fit in with this pattern. Similarly, when we have something to a negative power, like we saw here, right, 2 to the negative 1, it meant I had 1 power of 2 in the denominator. 2 to the negative 2 meant I had 4 in the denominator, which note that 4 is 2 squared, so that is to say I have 2 copies of 2 in the denominator. So however many copies you have, that negative exponent means take the positive number of copies and put it in the denominator. And the way that we can think about this, to use a little fancy math term here, is we could take the reciprocal of the expression. The reciprocal here means taking 1 over something. So a negative power just means the positive powers in the denominator. Again, this is going to have a lot of significance when we get into our section on scientific notation, which is mostly what we'll be interested in for this course. So we've introduced exponents. Now we need to fit this thing into the context of all the other different operations that we talked about. And there is a standard way that we do so. So there's a standard procedure for evaluating these order of operations. And you may have heard it referred to as PEMDAS, or just as the order of operations. So as the name sort of suggests, we start from left to right in this expression. So the very, very first thing we do is we start with parentheses. So we're going to look within the parentheses and compute any operations within those parentheses. After we've looked at things within the parentheses, we are going to go ahead and look at exponents. So we are going to take things to whatever power they're being expressed to. Next up, we have m and d, and those actually happen at the same time as one another. So multiplication and division happen as part of the same step, and they go from left to right. I always see these things shared on like social media of like, no way you can guess what this number is, and then people get into Facebook arguments about it. Anyhow, they're wrong, and the way that you actually do it is you have to go from left to right and compute the multiplication and division sort of in that one step. Addition and subtraction work the same way. They actually happen at the same time as one another in an order that is left to right. Again, this is really just a convention. It's just so that when I type these things into a calculator, it has some way of processing it. You can always make things more clear by putting in more parentheses, then it'll make it very, very clear which numbers are associated with which. But since we're going to have to be working with various expressions here, we want to make sure we're comfortable and confident with using these things. Because again, there's this computer science idea of garbage in, garbage out. If you feed your calculator the wrong input, it will give you a number. It will compute it correctly, but it will be meaningless because you haven't told it what you actually want to do. So when I have -7 to the 0 power, well, we mentioned that anything to the 0 power is going to be 1. So any number to the 0 power works out to be 1. Again, if you were to do this in your calculator, you could do this, but you have to use parentheses. Be careful. So you take -7. The button for exponents, again, it might vary based on your calculator. You might see something like x to the y, or you might see this little caret symbol. So I'm going to use this thing here. So the caret symbol, take this thing to the 0 power, I get 1. Note it actually gives a little decimal place there, like we mentioned in the last section. Now let's say I look at something that kind of looks a little similar. 2 times x to the 0 minus 2 to the 0. So here's where the order of operations part comes in. So there's no parentheses, so we'll skip that part. But the first thing we're going to apply is exponents. When I look at this expression, 2 times x to the 0, that 0 power, because there's no parentheses around the 2x, that 0 power is only being applied to the x. So that x to the 0, as we mentioned, anything to the 0 is 1. That 2 times x to the 0 will be 2 times 1. Now the 2 to the 0, again, as we mentioned, anything to the 0 power is 1. Because exponents happen before multiplication, we have to simplify those things first. Now we have 2 times 1 minus 1. Well, 2 times 1 is just 2. Multiplying by 1 doesn't change anything. And then we have 2 minus 1, so now we can go ahead and do that subtraction. That's not what it equals. There we go. It equals 1. Sometimes your brain does funny things. There we go. 2 minus 1 is 1. What about 6y to the -2? Well, what did we mention on the previous page? We mentioned that negative exponents mean positive powers in the denominator. So when I have 6y to the -2, I can rewrite this as a positive number of powers of y, specifically positive 2 powers, sorry, not of y, of 6y. So this whole thing is being taken to the -2, so that whole expression is going to be taken to the 2 in the denominator. So this expression we have is 1 over the quantity 6y squared. Well, now we bring back in our exponent rule that we mentioned on the previous page. When we square out 6y, we can square each part. Square the 6, we'll get 36. Square the y, we'll get y squared. When we like to express things in fractions, is because, again, that whole fraction versus approximate thing, if you actually try doing 1 over 36, you get this really nasty looking decimal, and if you round it, you've lost some accuracy, you've lost some specificity of this problem. So when we like to write things in fractions when possible. All right, now let's throw in some more stuff here. Let's say we have negative numbers and negative powers in here. So we're going to be taking -2x to the -2 to the 3rd power. Again, how does this work with order of operations? Well, we have 2 ways of thinking about this. One is thinking about doing those operations one by one. The other is to use these rules that we've talked about here. Now, again, with what's going on right now, there's actually kind of nothing to carry out per se, right? There's not like a subtraction or addition or whatever that I could do here, but what I can do is rewrite this by expanding it in a different form, right? So we can use those exponent rules we talked about. Well, the first thing we can note is we've got a product here being cubed. Well, when I have a product being cubed, I can think about that as being each part cubed. So I can cube that first part, the -2, what we call a coefficient, and I can cube that x to the -2 part. Well, what's this thing? So -2 cubed. So note I'm cubing the whole thing. So there's 2 parts to this. There's the numerical part, and then there's the negative part, the sign part. Well, when I take a negative times a negative, it becomes positive. And then if I multiply by a negative again, it becomes negative. So that result is going to be negative, and 2 times 2 times 2 is 8. So that number works out to be -8. Again, you can actually do that on your calculator. There's no shame in doing that. Better to have an accurate, correct answer here. So we got -8 from that. And then here we got x to the -2 being cubed. Well, you know what? Why don't I take one step to rewrite this thing? There's actually a couple of ways we could do this problem, but let's just try to remind ourselves what this thing means. When I'm taking x to the -2, that's really just a shorthand for saying 1 over x squared. And it's an expression that shows up often enough that we do like to have that as its own sort of notation. So x to the -2 means 1 over x squared. And now at this point, now we can think about this as being, well, I've got a fraction cubed. I can cube the top and cube the bottom. Well, 1 cubed is boring. It's just 1, right? Multiply 1 any times by itself, it'll just still be 1. And when I have x squared cubed, we multiply those 2 powers together, we will get x to the 6th. By the way, again, I kind of skipped over that step, but it's worth mentioning here. When I've got just a whole number times a fraction, you can always think about that whole number as being itself divided by 1, and then think about just multiplying across fractions there. Again, there's a little extra practice module in the Canvas course. If you're feeling a little queasy about some of this fraction stuff or decimal stuff, definitely worth spending some time to practice it, because it is stuff we're going to be using a lot in this course. Now, another thing we need to mention as we get into the next exercise here is that when we're working with exponents in the context of approximate numbers, we are going to use the accuracy of the base when it comes to choosing what is an appropriate thing to round to. How many significant digits do I have here? So let's say I want to evaluate this expression, -354 times 1.4 squared. Note the all-important directions to round to the appropriate number of significant digits and assume all of the numbers are approximate, which is to say they are subject to some amount of measurement error, and we need to keep in all of those rules that we talked about in the previous section. So this will be some more practice with this. So -354 times 1.4 squared. Well, first off, the computation part of this, again, we have calculators to do this sort of stuff. This is not the olden days. We can make our calculator compute this. And in fact, a lot of calculators, since squaring is something that happens so often, a lot of calculators will actually have a button that will just square things for you. So we're going to have -354 times 1.4 quantity squared. Now again, what the calculator tells me from this expression is -693.84. But this is more accuracy than is actually warranted based on the numbers here. So before I just call it a day and report that result, let's do the same thing we did last time and observe the number of significant digits we have here. So first off, this thing is going to have 3 significant digits because after all non-zero digits are significant. And same thing here, this thing will have 2 non-zero digits, so 2 significant digits here. And when we're squaring this thing, 1.4 squared, our rule says is we're going to use the accuracy of the base, which is to say we are going to report it with 2 significant digits. Well, now I've got a number with 2 significant digits times a number with 3 significant digits. Again, we are limited by the accuracy of the least accurate result when it comes to taking a product. So we are still going to be limited to 2. So we're going to need to report the result to 2 significant digits. So in that case, right, we have to start counting with this one. So the only ones that are significant are these 2, meaning we need to figure out which thing we are going to round this to. Well, we need to round the 9. Since the 3 is less than 5, it means we round down. So this will be -690. Note, I don't put the decimal point because I don't have specificity to the nearest ones, just to the nearest tenths, so that's the way we go ahead and indicate that. It actually makes a lot of sense that we use the accuracy of the base, because 1.4 squared is just 1.4 times 1.4. So if we have two significant digits times two significant digits, well, it's still two significant digits because that's the accuracy of the least accurate one. All right. So we have another kind of brief, weird segue a little bit into another topic. That is how the book chose to organize this, into another topic here, which is unit conversion, something we're going to do a little bit in this course. And chances are something that whatever technical scientific discipline you work in, you will probably have to do this sort of stuff. So I'm going to go ahead and start with this brief caveat here. I will not be expecting you to memorize any of this table when it comes to unit conversion here. However, what you will be expected to do is to be given a conversion factor and to use that conversion factor to convert from one particular system into another particular system. And it's important that we don't just simply use Google because we want to know this process of how I go from being in one system of measurement into some other system of measurement, because this particular system of measurement that you're working with, you might have to specify a very particular thing like, oh, we're working with these parts and these parts measure 2.7 centimeters or something like that. So that's sort of the process that we're going for here. So we've got a couple of different conversion factors that we're going to be working with here. So we'll just consult this table as a reference and do it in a couple of problems here. So here I've got an iPhone 12 is listed as having a height of 14.7 centimeters. Let's find the height in inches and note the directions. We're going to use the appropriate number of significant digits here. So to find the height in inches, we are going to observe here that 1 inch is 2.54 centimeters. There's a few different ways to approach unit conversion. I'm going to share the way that I like the most, which is to think about each of these things as being conversion rates. In other words, I'm going to start off with 14.7 centimeters, and I'm going to use the fact that 1 inch and 2.5 centimeters are the same to multiply by some factor here, by some rate, to get the units that I want. Well, we know that there's 1 inch in 2.54 centimeters. So if I have a fraction that has 1 inch on one part and 2.5 centimeters on the other part, then that's just 1, right? 1 inch over 2.5 centimeters is 1. Let me write that down. By the way, that is actually an exact measurement. I did a little Wikipedia lookup to figure out how that happened to be the case. There was some agreement made on that. Anyhow, you can do your own Wikipedia rabbit holes. The purpose for this thing here is we can observe that since there is exactly 1 inch in 2.54 centimeters here, we want to multiply by the factor that will get rid of centimeters. We talked about earlier in the section about how if you have the same thing in the top and the bottom, you can divide them out. So if I have centimeters here, again, you can think about that as centimeters being in the top. We could multiply by the conversion factor that had centimeters in the bottom, and then just use the numbers that we have here. So I've got 1 inch per 2.54 centimeters. Well, again, when you see that fraction bar literally means division. So the mathematical operation that's happening here is you're doing 14.7 times 1, and then dividing by 2.54. Well, of course, multiplying by 1 doesn't do anything. So really, we just get 14.7 divided by 2.54. And we get, of course, a weird, ugly decimal number. So now we have to figure out, well, what's the deal with the number of significant digits? We mentioned in the previous course, or the previous class, that exact numbers have no effect on the number of significant digits. So we're just going